whichever you think might be better addressed in the session, and we can take the rest on Slack. Okay, you can even start the live stream now, Bodhan.
Yeah, I'm starting.
Okay, and Japing, you can switch to your slides. While introducing you, you can have your slides. They're better to look at than my face anyway.
So I shared my slides. So can you see my slides?
Yes.
Okay.
Okay. We are streaming live. We are recording. Everything is okay, Bodhan. Should I start?
Yeah, everything's fine.
Okay. Okay, we'll start in a minute. It's 9:15 at 10. Okay. All right. Let's start. Hello, everyone. It's my pleasure to welcome you all to the award-winning paper session at the conference. This will work slightly differently than other sessions. In particular, the speakers will have up to 15 minutes to give their talk, after which we'll have about 5 minutes for Q&A. You can ask your questions through the Q&A feature in Zoom, or raise your hand at the end of the talk, at which point one of us can unmute you. And in case we are not able to address any of the questions, we will take them offline on Slack. And our host or our Zoom boss right now is Bodhan Kiva, also known as ACM Conference 7. And let's start with, let me introduce the speakers. So the first talk is on improved bounds and dramatically improved bounds for the sunflower lemma. The paper is by Ryan Alves, Shahar Lovet, Kevin Wu, and Japing Zhang. And Japing will give the talk.
Okay.
Japing, I'll mute and please start.
Okay. Thanks for the introduction, and thanks everyone for coming. Today I will talk about improved bounds for the sunflower lemma. Okay, so this is a joint work with Ryan Alves, Shahar Lovet, and Kevin Wu. Okay, let's start. In this talk, I will go through 3 parts. The first, I'm going to introduce the sunflower structure and also sunflower lemma. The first, the sunflower lemma. And in the second part, I'm going to tell you our improved sunflower lemma bounds. And in the third part, I'm going to tell you discuss some open problems and the future directions. Okay, so let's start with some simple definitions. So in sunflower structure, we're going to talk about set. Set system. A set system is just a collection of sets. Okay, so we call F a W set system if each set in F has size at most W. So we're just talking about sets. Okay, then what is the sunflower structure? The sunflower structure was introduced by Ederson and Rado in 1960. Okay, given a collection of sets S1, S2 up to SR, we call them an R sunflower if for any I and j, the intersection of Si and Sj is exactly the intersection of the whole sets. Okay, by the way, in the original paper of Ederson, they call it a delta system. In a later paper of Franco and Deza, they renamed it as a sunflower. Okay. So let me give you an example. Let's say we have 4 sets. S1 is equal to x1, S2, x2, and x3, and S2 is equal to S3, S4, and X5, and S3 is X3 and 6, and X4 is X1 and X4. Okay, so basically, if we choose the first 3 sets, S1, S2, and S3, then it is a 3 sunflower. Why? Because if you pick any 2 of them, the intersection is exactly X3, and this is also the intersection of the first 3 sets. So X3 is the common intersection. However, if you pick S1, S2, and S4, then this is not a sunflower. Why? Because the common intersection of these 3 sets is empty set. There's no element below all of these 3 sets. However, if you take X1 and S2, the intersection of these 2 sets is X3. Therefore, this is not a sunflower. So basically, this is just some examples. Okay. And what is the sunflower lemma? In this paper of Ederson and Rado, they proved the first sunflower lemma for any R, and for any fixed R, any W set system of size at least W factor times R-1 to the W contains an R sunflower. So think about a constant R. So if R is a constant, then this bound is roughly W to the W, because this is the order of W factor. This is the main bottleneck. And in this paper, and they also believed their lemma is not optimal. And in further, they have this sunflower conjecture. It says for any R, there exists a constant. This constant depends only on R. So there is no dependence. So this constant does not depend on W. So there exists a constant C such that any W set system of size at least C to the W contains an R sunflower. So you can see the main gap between sunflower lemma and the sunflower conjecture is W to the W versus constant to the W. And the sunflower conjecture has been open for 60 years. Even for R is equal to 3, we don't know, we don't have any, we don't know how to prove it. Okay, so basically this is the sunflower lemma. And sunflower lemma is a structure about sets, and is a kind of simple structure. So however, it turns out it has so many applications in both theoretical computer science and also has applications in combinatorics. So let me try to give you tell you a little bit about some applications. It has applications in monotone circular lower bounds. This is a nice paper by Nogalon and Popana. And also it has applications in fixed parameters complexity. And also it has applications in matrix multiplication lower bounds. And also it has applications in data structure lower bounds. This is a pretty new application. And also it has applications in graph cards. Okay, so this is relatively new results. Okay, and of course it has applications in combinatorics, because this definition was introduced in combinatorics. Okay, and it has many more applications. Okay, so then what is our new result? So basically we give improved sunflower bounds. Okay, let me remind you the original original bound. So for any R in any W set system of size at least W factorial times R minus 1 to the W, then it contains an R sunflower. Okay, by the way, before our result, what was the best result? Okay, so because this conjecture has been open for 60 years, so a lot of people tried to study this problem. However, the best result was the result by Kostuchaka in 2000. He proved any W set system of size at least the W to the W minus little OW contains 3 sunflower. So basically the main improvement was the W to the little OW term. Okay. So what is our result? In this work, we proved for any R, for any fixed R, so for some constant C. Okay, I want to mention this constant C does not depend on R, and also does not depend on W. This is just the universal constant. There is for some constants, any W set system of size at least C times R to the cube times log W times log W contains an R sunflower. So this bound looks complicated. Let me try to simplify it. Think about think about the constant R. This bound is roughly log W to the W. Again, the improvement here is from W to the W to log W to the W. Okay. So in some subsequent work of so there were 2 subsequent works. One is by Frankstone, Khan, Narayanan, and Park. And the second one is by Anup Rao. So by combining these 2 works, okay, so we can further improve this bound. So basically, this is the best bound so far. Okay, so for any R, so there is for some constant C, any W set system of size at least C times R times log W to the W contains an R sunflower. Okay, so basically they can improve the dependency on R from R to the cube to R, and also they can shave the log W term. Okay, so by the way, I want to mention this bound is this bound is pretty tight in our framework. So because in our proof, we prove something even stronger than sunflower. We prove the structure which is called the robust sunflower. And in our paper, we show that log W turn is tight for the robust sunflower structure. So basically, because in our framework, we prove that something called robust sunflower, and then sunflower is just a corollary from the robust sunflower. And the log W is tight for robust sunflower. Okay, so because we have done now we have an improved sunflower lemma bound, and of course we could have many new applications. For example, based on this approach, a nice paper by Frankstone, Khan, Narayanan, and Park, they give a proof of the fractional expectation threshold conjecture from random graph theory. Okay, it gives many applications in random graph theory, and also it gives new monotone circular bounds. This is a nice paper by Kavala, Kumar, and Rossmann. And also it gives an improved lifting theorem from communication complexity. Okay, so this is a paper by Shahalovat, Ragumeka, and I. And also it connects to the tight bounds of the DNF compression. It's not a direct application, but all of this approach is already connected. This is a paper by Shahalovat, Cohen, and I. This paper is also published in STOC this year, and Cohen gave this talk 2 days ago. Okay, so okay, and it could have more applications. Okay, let me try to mention some open problems and future directions. Okay, so the first obvious question is, could we confirm the Adolf sunflower conjecture? Okay, again, the gap between our results and the sunflower conjecture was log W to the W and the constant to the W. And it seems our framework has a barrier to break this log W term. Okay, so the second question I'm interested is, could we prove the expectation threshold conjecture? And the next paper of FKMP, they proved fractional version of expectation threshold conjecture. And this is also a nice conjecture. And also, okay, so I'm also interested about this question. Could we further improve the lifting theorem? So because the reason is that I'm really attracted by communication complexity recently. Okay, and also could we find more applications in both theoretical computer science and mathematics? I believe there should be a lot of applications. Okay, by the way, so this is just a very short talk. There were two long talks online. One is by Shahalovat at TCS plus, and also the second long talk is by me, and it's at IIS talk. Okay, thanks.
Okay, thanks, Japeng, and congratulations again on the Best Paper Award. Can you see the questions from the audience?
Okay, so yeah, I can see the first question from Celio, and is the current best dependency on R known to be tight? Yes, this is tight. Okay, the only thing is unknown is the constant C. The constant C is not tight. Otherwise, all of these things are tight for robust sunflower. Okay. Okay. So the second question is by Hanling Ren, and can you explain what is the robust sunflower? Okay, so the robust sunflower, so intuitively is the idea to find a to try to define the disjoint set in this set system. So in our proof, we define the pseudo-random condition, and we showed under this pseudo-random condition, we can find the disjoint set in this set system. So, so high level in disjoint sets is also kind of sunflower because you get a disjoint set. Okay, so robust sunflower is related to disjoint set. We want to find the disjoint set in this set system. But on the other hand, we can show an example which is pseudo-random enough. We can show a large set system without disjoint set. Okay, so what exactly is the lifting theory? Okay, lifting theory is more related to communication complexity. So basically, this is the idea to convert a decision tree, convert a function with a high decision tree complexity or high query complexity to a two parties version with high communication complexity. So this is a lifting theory from communication complexity. Okay, so can you very briefly explain how the proof works? Okay, so the proof is the high level idea is that we define a pseudo-random condition is the which is called the spreadness. So we call a set system is spread if there is no common pattern. Say for example, if disjoint set, if you give a bunch of disjoint sets, then there is no common pattern. Pattern. So for example, on the other hand, for example, if a set system, each set contains a common element, for example, x1, then this is not pseudo-random. Then this is so we use a spread to capture this thing. So we say set system is spread, then this is not. Then this is pseudo-random, and we showed any spread set system contains disjoint set. So this is related to robust sunflower. And on the other hand, if so, our proof is the following: if a set system is spread, then it contains disjoint set. Otherwise, we can find a common pattern, and then we can do a restriction. We can do an induction to this subset system. I mean, the subset system is all of the sets contains this pattern. If it is common pattern, then this subset system is also large. Base case. Space R instead, which is cannot work with. Okay, so the next question is if the spread lemma works with a base R times log W from Rouse results, and you have yes, in the Rouse paper, in Rouse paper, this the spread lemma works with a base of R times log W, and in our paper we have to use R to the cube times log W times log W. So basically. So it depends on the base. So yeah. So our the spread lemma in our paper is slightly worse, and R to the cube and log W. So that's the reason we get a bound such as R to the cube times log W times log W to the W.
Okay. We still have a couple more minutes in case anyone else has a question. You can also raise your hand if you want to be unmuted and ask it verbally. Yeah, there is a question from Samir.
Okay.
Yeah, I just want to remind everybody that the best paper awards will be given out at the business meeting today. So both the authors and attendees may want to attend that. Thank you.
Any other questions or comments? Okay, then maybe we can kind of switch slides. Siddharth, can you start sharing your screen, and then we'll start in a couple of minutes or maybe a minute or so.
Yeah, I stop.
Just a reminder that there's also a Slack channel. So if you think of any questions later, please sort of ask them in the Slack channel.
Hi, Mother. Is my screen visible?
Yes, the screen is visible. I can hear you well. Okay. All right. Our next paper, which is also the winner of the Best Student Paper Award, is by Siddharth Bhandari and Shoyantan Chakraborty, both from TIFR, and Siddharth will give the talk. Siddharth, whenever you're ready.
So can I start? Yeah, sure. Hello, everyone. Welcome to this talk on perfect sampling of colorings from graphs. And this is joint work with my colleague Shoyantan Chakraborty at TIFR Mumbai, and I'm Siddharth. And although it might look like I have borrowed the title template from the last talk, that is not the case. So moving on. So let me jump right into the problem statement. So we are given a graph G of maximum degree delta on n vertices, and we are prescribed a set of colors K. And what we are interested in is the set of all proper colorings of the graph, which I'm denoting by script C. And by a proper coloring, I just mean a vertex proper coloring. So any two adjoint nodes receive different colors. And I'll be interested in the uniform distribution over script C, which I'm denoting by pi. So pi puts equal weight on all proper K colorings of the graph G. And what is our task? Our task is to sample efficiently and exactly according to pi. So what do I mean by efficiently? By efficiently, I mean anything which works in expected polynomial in the input. And the emphasis is on the word exactly. So unlike approximate sampling paradigms where we are happy sampling from close to pi in total variation, here we need to produce a sample exactly according to pi. So once again, we are going to design an algorithm which will take some random coins. Which will take some random coins, and its output will be distributed exactly according to pi. But in general, it is NP hard to determine if script C is empty or not. So just to sort of even have a chance of solving this question, we sort of assume that K is greater than C times delta for some C greater than 1. And you can see that if K is larger than delta plus 1, this sort of already ready coloring threshold. So at least we know that script C will be non-empty. And another thing I would like to point out is that the naive accept reject doesn't work here, as the number of proper colorings divided by the number of K colorings is just too small, so it will take forever. And what is the goal? The goal here is to sort of design efficient algorithms that work with the lowest value of K. Somehow the algorithms we design have this feature that if they work at a particular value of K, they work at higher values of K, and we are after this minimum threshold. And the previous work to compare in this field of perfect sampling of colorings is by Huber, where he shows that as long as the number of colors is delta square plus 2 delta, that is some quadratic in delta, we can efficiently sample according to pi. And the current work brings this bound down to a linear function of delta, which is 3 delta. So that's the punchline of the talk. So now let me introduce a rather popular method for sampling colorings called Glauber dynamics. So it is just a Markov chain on the state space of all all proper colorings of the graph. And its stationary distribution is our target distribution pi. And how does Glauber dynamics behave? So it takes a coloring chi, and when we want to update the coloring chi according to a step of the Glauber dynamics, we first choose a vertex v uniformly at random, and then we simply copy across the curve for every other vertex but v. So to assign a color to the vertex v, we make a uniform choice from the set of all available colors. So if you look at chi nv, this sort of represents a set of blocked colors, because we cannot make a choice from chi nv, as that would lead to an improper coloring. So we make a choice outside chi nv, say C, which happens yellow, and then simply assign yellow to the vertex v, and we get a new coloring chi prime. So that is how simple the chain Glauber dynamics is, and this is the underlying chain in all our algorithms. So moving on, I would like to contrast some results between approximate sampling and perfect sampling now. So in approximate sampling, the first result to sort of state is by Jerem, where he shows that if the number of colors is larger than twice the maximum degree, you can efficiently approximately sample from pi. So approximate sampling is approximate sampling is just the paradigm where we are happy sampling from a distribution which is close to pi in total variation. And the next result, which I would like to state, is by Bublé and Dyer, where they reproved Jerem's result using a path coupling framework. And skipping a lot of work in between, Vigoda had a breakthrough result where he showed that actually you can sample efficiently even when K is like 11 by 6 times delta using flip dynamics. And very recently, Chen, Delcourt, Moitra, Perarno, and Postel have managed to beat that threshold as well. On the other hand, the fact that perfect sampling is at all possible is intriguing, because the naive accept reject doesn't work, and the approximate sampling algorithms also don't work because they typically have a log 1 over epsilon dependence in the running time, where epsilon is a total variation distance, and we would have to set it to be 0. But Huber showed that indeed, if K is some quadratic in delta, then, sorry, I don't know why this is happening. If K is some quadratic in delta, then we can efficiently sample. And very recently, Feng, Gu, and Yin were able to improve Huber's bound. However, the bound still remains quadratic in delta, and there's another remarkable result of Liu, Sinclair, and Srivastava, where they actually show that as long as k is larger than 2 delta, there is a perfect sampler. They actually show there's a deterministic approximate counter, but that implies a perfect sampler. Whenever, but their running time is sort of dependent on delta in the exponent, so they require bounded degree graphs. So for general graphs, we were still stuck with the quadratic barrier, and that is what the current work addresses, and we get a bound of k larger than 3 delta. So moving on, now I'd like to introduce a little bit about perfect sampling. So the general question to ask here is that given a Markov chain P with a stationary distribution pi, can we exactly sample from pi somehow using the Markov chain B? So this question was beautifully answered by Prop and Wilson in '96, where they introduced this coupling from the past framework. And the idea behind coupling from the past is to just jointly evolve a Markov chain for each state in the state space omega from minus infinity to 0. And I know this sounds a bit absurd, but just bear with me. So what are we trying to do? We are trying to jointly evolve one for each state from minus infinity to 0. And if our joint evolution is reasonable, that is, it gives some chance for two chains to coalesce, then by t equal to 0, we do expect that all the chains would have coalesced to a unique state omega star. And the algorithm just asks you to output omega star. So it's a very simple algorithm. I don't know why this is, sorry. And the claim is that omega star is actually distributed according to pi. The rough intuition is that since each chain has had infinite time to evolve, it should be its stationary distribution, which is pi. And I would like to point out that this is a which you and all the minds when you try to change algorithms in space. So this was a big, although it's simplicity might say otherwise. Anyways, so now I would like to present the coupling from the past framework a bit more pictorially. So we have been making a noise about revolving chains from minus infinity to 0. So I'm sort of imagining minus infinity ahead in time all the way up to 0. And the way we evolve these chains is with help of our update function. So the functions are random functions from omega to omega with just one property that you track little omega. It looks like the whole thing has been followed. So then we have after the first index t, so that when we compose functions u minus 1 u minus t constants, that is what the and so for instance in this case we might try some I to 0 where the so initially the images of set and we apply these
Siddharth, sorry, we couldn't hear what you were saying about this slide. The voice was breaking up. Sorry to disrupt, but could you try again?
Hello? Yeah?
Yeah, we can hear you now. Yeah, we couldn't hear what you said about the current slide. Can I ask you to just start from that slide again? Sorry.
About from this slide?
Yeah.
Is this a yeah? Okay. Never mind. So I'm just trying to introduce coupling past. We want to evolve chains all the way from minus infinity to 0. So I'm just writing minus infinity on the left here, and we are evolving the slides all the way to 0. And the way we do this is with help update functions UIs. And the property that the UIs little omega, it looks like I followed the Markov chain. And what the CFTP algorithm then asks us to do is find the first time index t such that u minus 1 all the way u minus 1 comes with u minus 2 compose all the way up to u minus t is a constant. And so in this diagram, it might be that we start checking this at step I. So we start the full image. As we apply the function, we get the images to shrink. And it might happen that the images have not shrunk by t equal to 0 to a singleton. Then we go further back in the past and we sort of try at a different time interval. And the first time that we do find that the images have shrunk to a singleton, we output that unique element omega star. That's the coupling from the past. algorithm. And now let me just present the CFTP algorithm for colorings. So for colorings, we are going to use the underlying chain to be global dynamics we had discussed before. Our update function will be sort of given by these tuples sigma I bi. So each update is defined by this sigma I bi. And what is
Siddharth?
VB is just a uniform. Yeah.
Sorry
Hello?
to disrupting. We still seem to be having audio issues. We can't quite make out what you are saying. Can I ask Shayantan to switch and see if he can continue?
Yeah, that's
My
also
apologies.
fine. Yeah, I don't know why this is happening. It was good in the testing. Can I reconnect and try?
Please, sure.
Yeah, 1 second. Hello.
Yes, we can hear you.
Okay, great. So 1 second, let me try to share my screen again. So can you view the slides now?
Yes.
Okay, so yeah, I'll try to end soon after. So yeah, I was saying the update functions are described by the sigma tuples in the CFTP or the colorings. The sigma is random commutation colors, and D is just a randomly chosen vertex. And maybe sort of interpreted. It's just so if you take a coloring chi, the update UI produces a new coloring chi prime, which just differs at the vertex V. And the way it differs is that it looks at and chooses the first color which is available.
Shayantan, oh, sorry, Siddharth. Sorry, we're still having audio issues. Can I request Shayantan to please take over at this point?
Okay, sure. Okay. Maybe if I don't use the style, is it okay? I don't know where Shantan.
I'm here. Let me take over.
All right, sure, that's good.
Madhur, can I share my screen?
Please do.
Okay. It's not allowing me to. Siddharth, stop sharing your screen. Okay. Okay. Hi, everyone. Sorry for the issues. Just 1 second. Yeah. So I think Siddharth's slides kind of gave out here. So what he wanted to say was the following. You guys can hear me, right? Madhur, can you? Am I audible?
Please,
okay.
Yes, please continue.
Okay. So the point is that CFTP works in the following way. That we initially sample independently these update functions independently across time, u-1, u-2, u-3, and so on. And we will start updating from some negative time, say minus I. Okay. So I'm going to apply the function u minus I to all of the members of the state space at time minus I. Then I'm going to apply u minus I plus 1 to the image of u minus I, and so on recursively. Now the point is that at t equal to 0, I'll check whether the image of this long update has coalesced to a single element or not. If it has, just output that element, and if not, what we're going to do is just go back in time and start from say time minus capital T. So again, I'm going to apply u at minus capital T to all the elements in the state space and continue as before. One comment is that at time minus I, we will have to reuse the functions u minus I at minus I plus 1. I'm going to reuse u minus I plus 1, and so on and so forth. And the point is that at some point after going back some amount of time, if at time 0 the image actually becomes a singleton set, then we can just output that sample, and what Prop and Wilson proved were that this sample is perfectly distributed according to the stationary distribution of the chain. So for colorings, the way this works is our update functions are actually vertex sampled uniformly at random, and permutation sigma also sampled uniformly at random on the set of colors. So what happens is that suppose chi is some coloring in the image up till time t, in the image of the long update until time t. So what we'll do is we'll look at the vertex prescribed by the update function at the time, say I, sorry, this should be minus I, this is a typo. So at v of minus I, we are going to look at the first color in sigma I that is not in the neighborhood of v. So in this example, that color is yellow, and we simply recolor v as yellow. Okay. And it's pretty easy to see that this is actually for every chi in the image till now. This actually follows Glauber dynamics. The issue is that we cannot keep track of an exponential number of these colorings, and we don't really know how to argue about the time it takes for this chain to coalesce. So this is where the bounding chain structure comes in. Is that So what Hubert proved with the bounding chain was that this bounding chain is a polynomial size structure which contains information about these exponentially many colorings. Okay, and and essentially what it is at every vertex the bounding chain will assign, instead of single color, it will assign a list of possible colors, and every coloring chi up till the point t will be contained by these lists. I'll make precise what I mean by that. But essentially, the takeaway from this is that if at time 0, the lists at every vertex reduce to a singleton, then we can, with probability 1, say that this sample, the sample which the bounding chain contains, is actually a correct sample, a sample that is perfectly sampled from the stationary distribution. Okay. So what Hubert proved in his paper is that for t something like delta times n log n, the probability that if you run this bounding chain process for time t, the image reduces to a singleton is strictly greater than half. So on expectation, you just have to run the CFTP framework twice for this algorithm to succeed. So just let me very briefly tell you what I was saying earlier, so get into some detail about the bounding chain. So what the bounding chain does is it maintains this particular invariant, that suppose up till time t we have updated up till time t, and this coloring chi is in the image of these updates. Okay, and so suppose this chi at some vertex v, suppose it assigns the color green. The invariant is that at this time t, the bounding chain assigned to the graph, the list that the bounding chain assigns at the vertex v will always contain this color. And this is true for every chi that is in the image of this large update. And we maintain this invariant throughout the evolution of the chain. So essentially what the bounding chain is it's an upper bound on all possible colorings that could have occurred up till that time, given these update functions that we have. And the remarkable thing is that this bounding chain is a polynomial size structure that contains a description of exponentially many colorings. Okay, so let me get into some detail very quickly about Hubert's bounding chain. So Hubert's algorithm works in 2 phases: the warm-up and the coalescence. So the warm-up phase will last for something like n log n time, and the coalescence phase lasts for delta times n log n time. So the warm-up phase is actually very simple. The first question is, how do we start? At time minus t, how do we exactly start? So at time minus t, what we do is at every vertex, we will assign the complete list of colors. So in this case, the complete list of colors is 5, let's say. It's black, green, blue, yellow, and red. Okay. And at every update in the during the warm-up phase, we will select a vertex uniformly at random according to our update function. And we will assign to that vertex the first delta plus 1, in this case 4 colors that occur in sigma at that time, right? So at the end of n, this n log n time with using coupon collector, we can say that with very high probability, every vertex has a list of size 4. And the bounding property, the bounding invariant is very clear. Because see, since we are assigning delta plus 1 colors to every vertex, there is at least...
Kindly you could end soon. The time is running out.
Oh, sorry. I just have one more slide. Sorry. So the point is that, yeah, this delta plus 1 list of vertices will always contain at least one color with which any chi contained by the bounding chain can update itself at V. But the punchline happens here in the coalescence phase where we where we can update in two possible ways. One possible way is that if we suppose we are updating at V and we find that the first color contained in sigma is not in any of the lists of the neighbors of V, then we simply assign this the list of V as a singleton color. Okay. And if not, we just give up and we are going to update using the first delta plus 1 colors. This step, this extra step of assigning a single color is actually progress. And as you can tell by the diagram here, that whenever k is large, the probability that this scenario happens is larger. And when k is small, this is an unfavorable event. But if you look at Huber's analysis, and this WT actually is a set of all vertices with list size 1 at time t. So what Huber proved is that this quantity size of WT, this performs a random walk on 0, 1, 2, n, and with 0 reflecting and n absorbing. And if k is greater than delta square plus 2 delta, and the coalescence phase is like that's t prime, that's for delta times n log n, then this probability that after running the chain for t steps, the bounding chain, all the lists of the bounding chain are 1 is strictly greater than half. And this is essentially where we get all our savings. That is, Huber's analysis is a worst case analysis. Okay, this thing, it's actually this delta square comes from max list size times delta. And in our algorithm, what we have been able to achieve is the following: that this max list size, during the coalescence phase, we have been able to bound to 2. And our algorithm, by the way, also runs in 2 phases. But in the coalescence phase, every list size is almost 2 in our algorithm. And in the warm-up phase, what we simply ensure is that we bring down the list size of every vertex down to 2. And that is essentially where we get all our savings. I don't think I have any more time. So thank you for being here.
All right.
Okay.
Thank you for the talk. Congratulations again on the Best Student Paper Award to both Siddharth and Shantan. Sorry about the technical issues and my apologies for making you switch midway. Can you see the questions from the audience?
Yeah.
Either of you can answer. Yeah.
Actually, I don't know any result along these lines. Maybe Siddharth might know. I'm not sure entirely. So
just to clarify, the question is by Clement. What about approximate sampling, but with a stronger guarantee than total variation? Like Kullback-Leibler and multiplicative guarantee on the probabilities or something other than that?
Yeah, that's a very good question. Actually, I'm not aware of any such results for colorings. So yeah. I'll have to think about this.
Yeah.
There are also 2 raised hands. I'm sorry I didn't allow people to talk during the session, but there is a hand by Christoph Onak. Christoph, you can speak now if you want. Christoph? Okay, maybe we can go to Abhinav, who also raised his hand. Abhinav Garg. Abhinav, you're allowed to speak now. You can just unmute yourself and ask if you have a question.
Okay. I'm not sure how relevant this is, but I remember that the earlier version of this paper had like a slightly worse bound. I think it was
delta square over log delta.
Yeah, so I was just curious, like what what you changed to got like the
we essentially changed the warm-up phase. So in the previous paper, the warm-up phase was much more complicated, and we used pigeonhole principle kind of argument there. But it turns out that the main argument that we used in the coalescence phase, we could push it even further to to actually get better bounds for the warm-up phase as well. And that's why the new paper is slightly simpler when it comes to the warm-up phase.
okay, thanks.
And there are two more questions in the Q&A. Can you see them? Or?
Yeah. So which warm-up phase, Huber's or ours? Okay. So the main idea in the warm-up phase, both in the warm-up and the coalescence phase, is kind of the same. And what we call it bias sampling. Essentially, we want the bounding chain to have lists of size 2. Okay. So imagine that every neighbor of the vertex V that you're updating has lists of size 2. Let's say somehow you manage to do this. Okay. And we want to maintain this condition. So what we do is we select two colors. One from, so for those of you who have seen the other videos, one from inside STV and one from outside STV. So and what we ensure is that any chain that is any coloring that is contained by the bounding chain is able to couple itself to the bounding chain by flipping its own random coin, such that it seems like the marginal of the update for that coloring is exactly according to the Glauber dynamics. And we have to fix these biasing probabilities properly. But it turns out that the only condition you need for these probabilities to exist is that K is greater than S plus delta. Okay. And since we since we somehow hypothesize that this S is at most 2 delta, that's where we get K greater than 3 delta. Things are slightly different in the warm-up phase, because in the warm-up phase, we actually want the list sizes coming down from K, like we're starting with K size list to 2. Okay, things are slightly different, but not too much. So essentially what we do is we fix a set of colors of size delta A, and the bounding chain at every vertex during this warm-up phase, what it does is the list becomes A union some color C outside of A. Okay, and again using the same this bias sampling kind of idea, we ensure that any underlying chain couples itself to the bounding chain properly by flipping its own coins. That's pretty much the main idea behind it.
Okay, Shantan, let's stop the live Q&A phase right now. I mean, we still have a few minutes before the business meeting, which is at 11. So I'll ask Bodhan to stop the recording and live stream. We will